Welcome everyone. My name is Goel. I'm a postdoctoral researcher at ETH Zurich. In this presentation, I will talk about a AAAI 2021 paper, The Importance of Modeling Data Missingness in Algorithmic Fairness, a Causal Perspective. This is joint work with Alfonso Amayuelas from EPFL, Amit Deshpande and Amit Sharma from Microsoft Research. As we all know, algorithms are being used in many applications of societal importance like criminal justice, hiring, university admissions, finance, healthcare, etc. And so it is important to ensure the fairness of these algorithms. This problem has received a lot of attention recently from different fields. And so now a standard high-level approach that exists for training fair machine learning classifiers is as follows. To train a classifier, the first thing you get is a big training dataset. For example, if you're training a classifier for making loan decisions, your dataset may look something like this. On the left-hand side, you see different feature values like prior credit history, salary, education, etc. for different individuals. And on the right-hand side, you see the observed outcome, whether the respective individual paid back the loan or not. What I show you here is the actual German credit dataset used widely in fair machine learning papers as a benchmark dataset. You would then carefully select a fairness metric that is appropriate for a specific application. Then you would take a state-of-the-art fair machine learning algorithm and apply it on this training dataset to train a classifier with fairness constraints. You'd finally deploy this classifier to make future decisions in the real world. So that sounds like a good approach, no? Unfortunately, this common approach proposed and shown to work on benchmark datasets in fair machine learning papers does not work in practice. There is no guarantee that this supposedly fair classifier that you obtain using a state-of-the-art fair machine learning algorithm will actually take fair decisions in the real world. And why is it so? The reason is missingness in the training data. What do I mean by missingness in training data? Consider two individuals with features x1 and x2 who applied in the past for a loan. Let's assume that the bank approves the loan application of the first applicant and denies loan to the second applicant. After some time, we would observe whether the first individual paid back the loan or not, and the features and the outcome for that individual would become part of the training dataset. On the other hand, for the second applicant, the true outcome is never observed, and the entire record goes missing from the training data. So if I can summarize that slide more generally in one sentence, training data, even if it contains objective ground truth outcome and infinitely many samples, is always one-sided due to systematic censoring by past decisions. This is one of the main reasons why unfairness problem occurs in machine learning in the first place. But surprisingly, this issue is almost always ignored while proposing solutions to the unfairness problem. And the result is that the fairness algorithms that seem to satisfy fairness on training data fail to meet those very same fairness guarantees in unexpected and dangerous ways when deployed in practice. Here I show you the results of some simulations with a state-of-the-art fair machine learning algorithm, which shows that the difference in false positive rates across two groups is very small on the training set. But there is actually 6% difference on a real-world test set. And this is not about a particular data set. You can change the data set, you can change the fairness metric also, you can change the algorithm and select some other algorithm with completely different underlying principles. The observations are the same. That is, all the algorithms fail to satisfy fairness on a real world test set, even though they satisfy fairness on training data sets. So as I said, most of the work in fairness literature ignores this issue, but there is some recent work that considers this problem. Most of these papers consider specific problem settings, whereas our focus in this paper is on general identifiability and its implications for fair machine learning. Before we get started, let me also give a very quick introduction to causal graphs. So causal graphs are basically probabilistic graphical models used to encode assumptions about the data generation process. So for example, if we want to represent the causal relationship between variables A, B, and C, and we assume that both A and B directly affect C, then we can use this causal graph to represent that relation. Now, when there is missingness in the data, Mohan and Pearl have proposed this very elegant framework to encode that missingness mechanism also in the causal graph. For example, let's assume that we have a data set about these same variables that we discussed earlier, A, B, and C, and the data set has missingness in the variable c. For some records, we observe value of c, and for the rest, the data is missing. There is one more column in this table, the R subscript c, which represents the missingness switch or the missingness mechanism for the variable c. Whenever this switch is off, we observe the data, and whenever the switch is on, the data is missing. To show this in the causal graph, we first add a node c star in our old graph, representing the variable c that we actually observe in the data, and c is the original variable. We add one more node here to represent the missingness variable R subscript c. Now, because c star depends on both c and R subscript c, we added two edges there. All the nodes that have been shaded are the variables that we observe, and the white nodes are the variables that we don't observe. Now, the first case here is this, where the missingness variable R subscript c does not have any incoming edge from any other node in the graph. This case is the classic MCAR, or missing completely at random case. In the second case, there is an edge from B to R subscript c. This is the case of missing at random because the missingness is affected by an observed variable only. And finally, we have the missing not at random case because the missingness is affected by the variable c itself. So this is some notation that I will be using in the rest of this talk. X will denote the non-sensitive features of individuals, Z will denote the sensitive attribute, D will denote the past binary decisions about the individual, Y denotes the outcome that we observe about the individual, and U will be unobserved features that I will explain a bit more later on, and Y hat is the classifier's prediction. Now, there are many definitions of fairness, but I'll mostly be focusing on two definitions here. The results can be extended to other definitions also. Demographic parity requires that the probability of the classifier's prediction being positive is same across the groups. And equality of opportunity requires that the probability of the classifier's prediction being positive, conditional on the true outcome being positive, is the same across the groups. Here, I take a simple causal graph that shows how the sensitive attribute Z, the non-sensitive features X, and the outcome Y may be related. Now, if we had a dataset generated by this causal graph, we could train a classifier that would predict Y hat and compare it to Y, the true outcome, to estimate through the error rate of the classifier. The equality of opportunity constraint is nothing but a special case of equalizing error rates across two groups. However, what actually happens is that we don't have this dataset. What we have is a dataset with missingness. Let's show this missingness in our dataset now, in our causal graph now. So in the past, there were decisions D taken about these individuals based on their observed features. It doesn't matter for the purpose of this slide whether Z affects D or not. Based on the decisions, we observe this partial dataset. Now, what we want to estimate to enforce equality of opportunity constraint is this probability. However, what the fairness algorithms actually estimate from the training dataset is this. The question is whether these two probabilities are the same. Let's see. So by definition, I can write this as this. It turns out that these two probabilities are actually not equal because Y hat is not independent of D given Y and Z, and we can use the D separation criterion to read this from the causal graph. And we can show a similar result for demographic parity constraints as well. The causal graph-based framework allows us to find more general and stronger results. To generalize the results, we note that most of the fairness algorithms require estimating one or more of the following probability distributions, so we can actually see through the causal graph framework what happens to these distributions when there is missingness in training data. And of course, there can be multiple types of missingness. To include all possible types of missingness at a conceptual level, we note that missingness may be caused due to past decisions that were either fully automated, human-made, or perhaps machine-aided. The first case is of missingness due to fully automated past decisions. I take a causal graph here similar to the one shown earlier, and I add the missingness variable D and the observed variable with a star sign. So we can show in this case that the conditional distributions that we estimate from the data are actually correct. So that's actually a good news. But if we look at the joint distributions, then we can show that not only are our naive estimates incorrect, but actually these distributions are non-recoverable. That is, no matter how many data samples are provided, there exists no estimator to get the correct probability distribution. Now I'm going to make a small change in our causal graph by adding an edge between Z and Y. This may be true if an individual faced discrimination after being given a loan or after being hired that affected what outcome we observed about them in the data. In this case, we can actually show that even the conditional distribution estimate becomes incorrect. The causal graphs considered in the previous slide are more suitable for censoring due to fully automated decisions. We now consider the case of censoring due to human decisions. Humans often use features while making decisions that are not recorded in the training data. We call such features as unobserved features. Here is an example. I take my old causal graph and I add a node for the unobserved features U. For example, a human judge may observe whether a defendant has come to the trial with his family or not, and this feature may affect both the judge's decision as well as whether the defendant reoffends in future or not. But since this feature may not be recorded in the training data, we call it unobserved feature. In this case, we can show that both the conditional and the joint distributions are unfortunately non-recoverable. We can make similar conclusions about censoring due to machine-aided decision-making, where an algorithm makes a recommendation D subscript A to the human judge, and the human judge takes final decision that D that causes missingness. So to summarize, we saw until now that recovering joint distribution of features is impossible in almost all cases of missingness caused by past decisions. On the other hand, conditional distributions, also known as risk scores, may be recoverable in some cases depending on the causal graph for missingness. The bad news is that both conditional and joint distributions are used in several state-of-the-art fairness algorithms. We also saw that in general, missingness caused by human or machine-aided decision-making is more challenging than that caused by fully automated decision-making. And finally, we should remember that a small change in causal structure may lead to very different conclusions. Of course, we did not cover all possible causal graphs in this presentation or even in the paper, but the main idea is that one can use this framework to draw similar conclusions for other causal graphs as well that are more suited for a given application. So what is the use of all these results so far? Well, the causal graph framework, in addition to formally recognizing the negative results, also helps in determining which distributions are indeed recoverable and how. For example, consider the multi-stage decision-making setting, more specifically a two-stage decision-making setting. In the first stage, the decision maker uses features x1 of the individuals to determine whether to promote them to the next stage or not. Then additional features x2 are observed for the individuals who go to the second stage, and then a decision about final selection is made. Again, using the causal graphs, we can reason about which distributions can be recovered from a training data that has missingness caused by such a two-stage decision-making setting. We can show that the conditional distribution P of y given x1, x2 can be easily estimated from the data, while the joint distribution P of x1, x2 is not recoverable. On the other hand, the conditional distribution P of y given x1 can also be recovered through a simple factorization trick. We can now use these observations to design a detail-free, decentralized, and fair algorithm for multi-stage decision-making setting. We show in the paper that the objective and the fairness constraints can be written entirely using recoverable distributions. The theoretical analysis of this algorithm is in the paper. Here I show the empirical comparison of the DF2 algorithm with a state-of-the-art Oracle algorithm that assumes knowledge of the joint distribution, non-recoverable joint distribution. As we can see, the DF2 algorithm achieves nearly the same utility under fairness constraints as the Oracle algorithm. I will now conclude this talk with three key takeaways. Number one, the probability estimates used in state-of-the-art fairness algorithms are not correct due to data missingness, and thus any fairness guarantee of their training stage does not hold in practice. Number two, causal graphs provide a useful framework to formally understand the implications of different types of missingness in training data. And finally, on an optimistic side, we saw that depending on the causal mechanism of data missingness and the application, we can actually design algorithms that are fair even with incomplete data without compromising the utility. I encourage you to read the full paper that contains more interesting results. The paper is available on my website. I look forward to your questions, comments, and suggestions during the live session, the poster sessions, or through emails. Thank you very much for your time.